Hi, good morning. This is our final coding folder. So I have divided into two sections. The first sections indicate the code multi-objective. So here mentioned the so many buses. I have already mentioned so many buses. So I have taken one example, bus number 16. So in bus number 16, so our main code is main multi-objective.m, and our fitness function is function01.m. So just verify that main multi-objective.m. So this is our code, the previous code only. So number of bus is 16 to create a ESS model, act as a generator and charger, PV connection and sizing. Then this part only we have changing because here now using SHAMODE. So here number of loop and number of solution, number of archery is 2 in the number of solution. Here number of variable is 1. So why we are using one means we have produced the random switching concept. So random seed based switching concept. When you clear to clarify in function 01 clearly mention, I have read this variable, this ring generator called a random seed generator. So I have shown example. And so if we generate rand 1 means each time it's produced different random number, but in the case I have using a seed example, I have using a seed is 1. Then I have used rand 1 0.4170. It's same for next case also. This both case is same, but I have changed the seed. It's automatically changing. So this is the main concept. So based on random seed changing, here generate the permutation. I have already did the code same way and switching connection. So here we have in load flow analysis, we have introduced two variable si and smax. So when you move on this subfunction 1, it clearly shows everything is same in previous coding. The only changes the measure S power flow of each branch, because the S is the power flow of each branch divided by their maximum capacity. So if we have maximum capacity means that voltage profile equal to assign 1. Otherwise this is a current voltage profile. It's having both branch data and their switching connection, tie connection data. So we have calculate in fitness function the value like where we have mentioned Si by S max. So here we have calculate S equal to Si by S max, and already we have shown that fitness 2 is variance of S. So another one is our constraint. Constraint means that power constraint should be in between. That means the voltage value should be in between Vmin and Vmax. So if the constraint is negative, it's obey. Otherwise, it doesn't obey. Okay, that's a procedure. So this is a code. Run main multi-objective.m. When you run this code, so I have here used SHAMODE. If you like SHAMODE underscore WO, no problem, just change here. So here we have assigned function 1 after function evaluation to create Pareto friend result. So in F1 we have indicated PL, power losses, and F2 indicates our LBA, load balancing index. Then actually what is non-dominant sorting or Pareto friend? The Pareto friend doesn't having single data, it's having so many data, 1, 2, 3, 4, 5, 6 data. So if you like this data, that means 1, 2, 3, 4. Fourth data, if you want like to identify the tie connection means, you just assign, here is a choose index. So if you want that fourth index means just assign 4. So it shows the values. What is the PL losses for that condition, and what is the value of load balancing index, and what's the value of final their tie connection switching. So what's the use of non-dominant sorting? Otherwise, this multi-objective means is a tunable because this PL and LBA is a independently controlled. So if you take one plant, so this plant is the loss is very important compared to LBA means. So very last point, that means this PL loss minimum point is this point. This point will be choose. Otherwise, you want to control both LP is minimum and PL is minimum means we have choose this point. So this is a standard procedure of this non-dominant sorting or multi-objective method. Okay, so this is for one case. The same case we have written in every bus system. Okay, now we move on our next coding, load modeling. So load modeling we are using a main test.m. So we have simply written all equations. So when you see the PDF, you understood there are three steps. One is load modeling. Another step is demand response modeling. Third one is solar modeling. So this is a case. So we have it doesn't give any example data. So first of all, we have industrial NP, NQ value, residential, commercial. Then we have only assign a random because we are creating a modeling. So we create a random data. Initially, we create a random real power, reactive power, and voltage profile data. Each and everything is in power unit. Then calculate the equation 1 to P1, Q1 for each and every condition. So it shows the value. So when you run this code, it shows ask change folder add to path means you just give change folder. Okay, this is a time. We have taken 24 hours. So initially we have randomly taken any of the PQ value. Based on this PQ value, the industrial, residential and commercial values should be changing according to NP and NQ. So this is the first graph we are just randomly generated. Then equation 15 modeling, that means demand response modeling. So they have given some equation. I think equation number 15. D0 is the initial demand. D is our predicted demand. E is the energy value. Rho 0 is the price. So rho 0 is the initial price. Rho is the current price. Then income and penalty. So we have assigned just random value. That means here also we have assigned normalized random value. Then see the plot. Initial customer demand and final customer demand. So it shows like this. So based on penalty and it's identify the optimal customer demand value. Optimal means efficient customer demand value. Then solar PV modeling. Already we know, so solar radiance model, it's depend upon the beta probability distribution function. So we have taken the beta probability distribution function, but this alpha value and beta value we have given from this equation. This mu and beta is the important parameters. Mu and sigma is the mean and standard deviation of these parameters. So that value we have calculated. After calculating these values, you just plot this beta distribution function. So this is a normal beta distribution function value. So x-axis this normalized value and y-axis is a PDF probability density function. Then we have calculated the PV model. Already in this paper number of PV model is 10 and their temperature, ambient temperature, everything. So we have assigned this variable. If you want like assign another variable, it's not a problem. We just assign what you have or what your PV model. Just assign here. After assigning this, we have show the solar power. That means solar power time as solar power. So this is we got. Finally PV generation criteria. So already they are using it based on this power factor only, tan inverse cos of PF. Only it's generate reactive power. So reactive power equal to active power into alpha m. So when you use this equation, you got this value, active power, reactive power. Thank you for watching.